So there's one special type of matrix that we should probably mention before moving on that we left out of the zoo, and that's a vector. And there's two types of vectors. So if you let m and n be any positive integers, we have a row vector, which is just a 1 by n matrix. It's literally just a row. And usually we don't write A11, A12 all the way to A1n. We usually write just A1, A2 all the way to AN, just to avoid needless indices. And we also have a column vector, which is just an m by 1 matrix. This is the vector that we'll normally be working with if we work with vectors in the future. And it's just we indicate it by a lowercase letter with an arrow overhead. And it's a column of m by 1 matrix, so it's a column of m numbers. And since we'll usually be working with column vectors, we will just adopt the convention that an m vector refers to a column vector with m components or entries. So you might think, why introduce this? So in Isaac Newton's Principia, so Corollary 1, he actually talks about vectors without using that word. And he defines a operation to add two vectors together. So let's transcribe it as it were. So he says if you have a vector, you can indicate a vector geometrically because it's an arrow. So in physics, everything's a vector. Almost everything's a vector. So displacement from point 1 to point 2, that'd be a vector. And we have another displacement from point 1 to point 3, that's another vector. So what Newton said, and I don't think this is his unique genius insight, someone else probably came up with it first, but his genius was to apply it to physics. He said, okay, so then construct a parallelogram, and their sum is just the diagonal, right? And if you want to do matrix subtraction, so A minus B, then you have B go the other way. Construct your whole matrix going the other way, and that's A minus B. For us, we're working in a pretty non-geometric setting. So the equivalent definition would be if A is equal to A1 all the way to AN, and B is equal to B1 all the way to Bn, then we will say their vector sum is the new vector whose first component is A1 plus B1, dot, 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 all the way to AN plus Bn, just component-wise adding all their components together. So that eats in two vectors, A and B, and spits out a third vector, which is their sum. And geometrically in 2 dimensions, it's exactly the parallelogram law. And there's one last useful tidbit about vectors that we will need before moving on. It's the dot product. So if we have two m vectors, u and v, their dot product is just taking the first component of both, multiplying it together, then adding it to the product of the second component of both, doing that all the way through to the last component. And geometrically, what this would be is if we had u, v, and they're separated by an angle theta, then this vector here, from here to there, is the magnitude of u, the length of u, times cosine of theta. And the dot product is just going to be geometrically the length of v times the projection of u onto v. So that's the length of v times the length of u times the cosine between them. Or, equivalently, it's u1 v1 plus u2 v2 plus dot 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 plus um vm. So it eats in two vectors and it spits out a number. And that's, well, the relevant vector operations for linear algebra at the moment. Now, vectors are so important and influential that arguably linear algebra could be presented entirely abstractly in terms of vectors. And we will see this actually later on, once we're done exploring the world of matrices. We'll repackage our results in terms of vector spaces, the collection of all vectors at a point. So that's going to be exciting, and we're going to talk about it, down the line. So, till then.